Okay, Schrodinger wave equation, time independent. Schrodinger developed a fundamental wave equation based on the de Broglie concept of behavior of electron in motion. The Schrodinger equation describes the wave properties of an electron in terms of its position, mass, total energy, and potential energy. The equation is based on the wave functions, which describes an electron wave in space. The equation can be written in many forms, or one of the ways is written as dava squared psi over dava x squared plus dava squared psi over dava y squared plus dava squared psi over dava z squared plus 8 pi squared m over h squared e minus b psi equal to 0. So we can write dava squared over dava x squared plus dava squared over dava squared plus dava squared over dava z squared psi plus 8 pi squared m squared e minus b psi equal to 0. So we can write Laplacian of it square psi plus 8 pi square m over h square e minus b psi equal to 0. What x, y, z is space coordinates of the electrons were with respect to the nucleus. And Laplacian square is the Laplacian operator, mass of the electron as Planck's constant, total energy of electron, the potential energy of electron, and kinetic energy, E minus B kinetic energy of electron. Psi, a mathematical function called wave function, it represents the amplitude of electron wave around the nucleus at various points in three-dimensional space. Derivation of Schrodinger wave equation consider a stationary wave associated with the microscopic particles like electrons moving in the x direction. The wave equation for the stationary wave is given by psi equal to sine 2 pi x over lambda, equation 4, where psi wave function acts as displacement of the wave along the x-axis, a amplitude of the wave, and the lambda wavelength. Differentiating the equation 4 with respect to x, we get d psi over dx equal to a cos 2 pi x over lambda and 2 pi over lambda. So d psi over dx equal to 2 pi over lambda, 2 pi a over lambda cos 2 pi x over lambda. Differentiating equation 2 with respect to x d square psi over dx square 2 pi a over lambda. That is the cos is the minus sine 2 pi x a over 2 pi over lambda. So we get d square psi over dx square equal to minus 4 pi square. Psi square is sine 2 pi x over lambda. From the de Broglie equation, lambda equal to h over mb, m mass of the microscopic particle, b velocity of particle. Squaring equation 4 on both sides, we get the lambda square equal to h square over b square, b square. Substituting the value of lambda square in equation 3, d square psi over dx square equal to minus 4 pi square h square over m square v square psi. Again solving, we get d square psi over dx square equal to minus 4 pi square m square v square h square psi, equation 6. Total energy, kinetic energy plus potential energy, so equal to half mv square plus v potential energy. So we can write half mv square equal to e minus v. Okay, I'm solving the mb squared equal to 2e minus b equation 7. From equation 6, d square psi over dx squared equal to minus 4 pi square m square v square over h square psi. So again, solving d square psi over dx squared equal to minus 4 pi square m square b square m square b square square. So we can write in case of m b square, the substituting the value of m square from equation 7 minus 4 pi square m 2e minus b over h square. So d square psi dx square equal to minus 8 pi square m e minus b h square psi. So again solving we get d square psi over d square plus 8 pi square m e minus b over h square psi equal to 0. Equation 8 is the particle is in the one-dimensional similarity, particle in the three-dimensional. So we get the equation 9 d square psi over dx square plus d square psi over dy square psi over dz square plus 8 pi square m e minus b over h square psi equal to 0. Since equation 9 does not contain time and it is to call time independent Schrodinger equation, the equation 9 is also written as da by square psi over da by x square plus da by square psi of da by y square plus da by square psi da by z square plus 8 pi square m e minus b over s square psi equal to 0 equation 10. So again, we can write taking common psi, da by x square plus da by square psi of da by square plus da by square psi of da by z square plus 8 pi square m e minus b square psi equal to 0. Question 11. So Laplacian operator square psi plus 8 pi square m e minus b over s square psi equal to 0. Question 12. Laplacian operator equation to be Schrodinger wave equation. Significance of Schrodinger wave equation determines the energy levels eigenvalue. It is the always quantized energy values of the system. These energies are called eigenvalues and they explain why atoms have discrete energy levels. Provide wave functions, eigenfunction. The solution psi x y z describes state of the particle. It contains all measurable information about the system. Gives the probability of distribution. The square of the wave function psi square gives the probability density of the finding of particle at the position. This replaces the classical definite trajectories. Foundation of quantum system. It is used to analyze important systems like particle in box, harmonic oscillator, hydrogen atom. Basic for modern physics and chemistry. Explain atomic structure, bonding spectra, properties of matter. Essential quantum chemistry, solid state, and nanotechnology. Significance of psi and psi square. Psi is the mathematical function called wave function. Psi square always have positive values. Conditions should be obeyed by proper wave function. The psi must be single value wave function and its derivatives must continuous, must finite. Total probability of finding the electron overall from plus infinity to minus must be equal to 1. Okay, probability of wave functions. The probability of functions are fundamental to quantum mechanics, describing the quantum states of particle of system, radial distribution function, angular wave function. Radial distribution wave function, let us take a sphere having the radius r. It is then divided into a number of concentric, have one center. Spherical shell having the thickness dr and the volume of the source concentric spherical shell is given by 4 pi r square dr. Radial distribution curves obtained by 4 pi r square dr psi square versus r is called radial distribution curves. 4 pi r square psi square dr is the radial distribution function. Psi square is radial probability and also written as r square in terms of radial distance from nucleus. R distance from the nucleus. Radial distribution curve for 1s, 2s, 2p, 3s, 3p, 3d are plotted as the following. If n the principal quantum number, L azimuthal quantum number, L 0 to n minus 1 for n 3. So L equal to 0 to n 3 minus 1 plus 0, 1 to SPD. We know that the number of peaks in the curves n minus L, so 3s subcell 3 minus 0, 3 peaks. Similarly, 3p, n minus 1, 2 peaks, and for 3d, 3 minus 2, 1 peaks. Features of radial distribution curve, the probability of finding the electrons is 0 at the nucleus are equal to 0. The most probable distance of finding electrons increases markedly as the principal quantum number n increases. The most probable radius for the probability of finding electron decreases slightly as the azimuthal quantum number L increases with n remains constant. Number of peaks present in the radial distribution curves Ns, Np, N, and Nd orbitals are equal. 1 is 2p, 3d. The penetration power of the SPD and F orbitals decreases in the order Ns, Np, Nd, and F, so that the s orbitals has highest penetration power, that is, it lies the nearest to the nucleus than the other orbitals. The region around the nucleus at whose probability of finding an electron is 0 is called node, and the number of nodes present in the radial distribution curve are equal to n minus 1, n minus 2, and n minus 3 respectively. Angular work functions. According to Bohr's theory in hydrogen atom, electrons always revolve around the nucleus at a distance of 0.529 Armstrong. But according to the wave mechanical approach, an electron can be found anywhere around the nucleus. However, the maximum probability lies at the distance of 0.529 Armstrong. This distance is called radius of maximum probability. The quantum numbers are the identification numbers for an individual electrons in atom. Principal quantum number, it describes energy of electron and most probable distance of electron from the nucleus is represented by n. For example, KLMN. Azimuthal quantum number, it is associated with the angular momentum of atomic electron and represented by L 0 to n minus 1. SPD of 0, 1 to 3. If L is the angular quantum numbers of subshell, the maximum electrons it can hold 2 to L plus 1, that is for L plus 2. Magnetic quantum number, it is the permitted orientation atomic orbitals space represented by M minus L2 plus L. For d orbitals L equal to 2, so for any subshells defined by L value 2L plus 1 values, M equal to 2L plus 1, 5 permitted orientations. Minus L2 plus L, so minus 2, minus 1, 0, plus 1 to 5 orientations. Similarly, for F's subshell, 2L plus 1, 3, so 7 permitted orientations. In quantum number, it represents motion of electrons, orbital information about direction of electrons or rotating clockwise, anti-clockwise, and represents plus half or minus half. Significance of quantum numbers, it gives distance of electrons, gives average energy, maximum number of electrons. Azimuthal quantum numbers gives the number of cells, maximum number of electron that is accommodated. Defines shape of soft cells. Okay, define the shape of soft cell, that is electronic cloud. It gives the number of orbitals present in the soft cell. Magnetic quantum number determines spatial orientation of the electron clouds, that is the orbitals, in the 3D. For S soft cell, L equal to 0, M equal to 0. For P soft cell and for this soft cell, okay, reasons for stability. Stability of half-filled and completely filled orbitals. Symmetrical distribution of electron. Symmetry leads stability due to lower energy, so that orbitals either have half-filled or full-filled, have more symmetrical and reduce energy and then increases stability. In case of chromium, see 4s1 this is the half-fill. In case of the copper, 4s1 it is the full-fill. Expected configuration 3d4 4s2, but observed configuration 3d5 4s1. Similarly, in case of copper, 3d9 and 4s1, 3d9 4s2. But in case of observed, the copper 3d10 4s1. Axis of energy in case of the 3d5, that is the axis of energy is the 4 types axis for first electrons. Similarly, the second electrons 1 to 3 and third 2 and fourth one the 1. So 10 times in the case of chromium in the electronic configuration uh, is 3d4. Then the electrons can be changed in the 6 ways. 1, 2, 3, 1, 2, and 1 to 6. Hence, the number of exchanges maximized when the chromium has half-filled this subcell. Two electrons with parallel spins have the freedom to get themselves an accurate exchange between their orbitals. This reduces the energy and called exchange energy. Okay, nuclear reactions. The reactions in which the nucleus of an atom itself undergoes spontaneous change or interact with other nuclei is called nuclear reaction. Types of nuclear reaction, fission reaction. In these reactions, a heavy nucleus like uranium breaks down into two or more lighter nuclei like barium, krypton, and neutron. After intermediate and large amount of energy is liberated. Nuclear fusion reaction. In this reaction, two lighter nuclei are combined or fused together to give a stable nuclei and large amount of energy is liberated. See, deuterium tritium is fused and produce the helium and neutron in energy. Elastic scattering. In this process, both ejectile and projectile particles are the same and conservation of kinetic energy is maintained. For example, kinetic energy of projectile, gain of energy of kinetic target nuclei plus kinetic ejectile. In elastic scattering, in this process, the projectile and ejectile are the same. Kinetic energy is not conserved. Photonuclear reaction. In this process, gamma photons access the projectiles. Gamma p atomic number and mass, gamma n atomic mass decreases. Radioactive capture, the particle on capture leads to the emission of radiation in the form of the one or more gamma photons. Half-life determination, the half-life of the radioactive element is the time required for disintegration of one half of the original amount of radioactive substance. Let an atom changes A to B, an initial minus X. The beginning takes to zero number of mole of radioactive substance. After time t, x mole of substance will have decay leaving A minus X. Hence rate is disintegration dx over dt Ka minus X, where K is the disintegration constant, K dt dx over A minus X. So on integration, we get Kt equal to minus ln A minus X plus C. So we get C equal to ln A, and solving we get K equal to 2.303 over T log A over A minus X. Let at any time half of the substance has disintegrated, so X equal to A over 2. So solving we get the half equal to K over 0.693. Group displacement law. On studying the natural radioactive series of elements, arrive at a set of laws called group displacement law. When alpha particle is emitted in radioactive chains, the atom number of products elements decreases by 2 units and atomic mass decreases by the 4 units. Alpha 34 to 35 to 31 decreases by 4 units, and the mass 90 decreases by 2 units. When the beta particle is emitted in the radioactive chains, the atomic number of product element is increases by 1 unit, and while the mass number of remains unchanged to 11, 82, 83. When a radioactive element is emits an alpha particle and beta particle successively, then the product and original elements are isotopes. When a radioactive elements emits positron beta plus E plus, the atomic number of the product decreases by 1 unit and products isobars. B plus. Radioactive series, thorium, uranium, actinium, and neptunium series. The radioactive series, also called as radioactive decay series, is the series of the elements obtained by successive disintegration of parent radioactive elements to a non-radioactive stable element. The series of elements obtained from thorium, uranium, and uranium-235, uranium-239 are natural radioactive series, while the series obtained from the artificially prepared neptunium-237 is called radioactive series. There are four series of radioactive series. Thorium series starts with uranium 232 and ends with lead 208. Uranium 4n plus 2 series. The parents uranium-238 is the starting parent radioactive elements undergo and form lead-206. Since the mass number of all elements in this series gives the remainder of 2, when divided by 4, it is called 4n plus series, where n is the integer it possesses longest half-life. 4n plus 3 and 235 lead 207. In this case, the Fourier series starts with thorium 232 and ends the late 208. Uranium 4n plus 2 series, uranium 238 ends with the late 206. Neptunium series begins with the found element series are not found in nature. It begins with the bismuth and terminates into neptunium 237. The mass number of all elements in this series gives the remainder and divide 4 and 4n plus 1 series. See in this neptunium series 237 neptunium. First of all, uh, and ends with the bismuth 209. Actinium series and starts with 239 uranium and leads 207. Okay, shielding or screen effect, the electrons present between the valence shell and nucleus are called intervening electrons. These electrons extend inter-electron repulsion. The nuclear attraction on valence shell decreases due to repulsion. The decrease in nuclear attraction on the valence shell due to presence of intervening electrons is called shielding effect. Factors affecting the shielding effect, the number of cells greater is the number of cells, the higher will be the shielding effects. For example, sodium shows greater shielding effect than lithium. Nature of orbitals according to wave mechanics, the penetration Nearness of the electrons in the orbital to nucleus, power of the electron is different. Orbitals of the given cell decreases in order, so penetration power Ns, Np, Nd, and Nf. Ns is the nearer to the nucleus, so greater penetration power. Application of shielding or screening effect. It explains the variation of atomic radius, ionized energy from left to right along the period and top to bottom, shielding down the group. Concept of shielding effect explain the cause of the larger difference in ionization potential on moving from alkali metals to noble gases in same period. It also explains the cause of similar atomic size of the elements of second and third transition series belong to the same group. This concept also explains the lanthanide contraction. It also explains irregular variation of atomic size and ionization potential element present in group 30. Diagonal relationship, it is the resemble of the properties of elements second with the diagonally opposite members allowing the third. See lithium, magnesium, beryllium, aluminum. Cause of diagonal relationship on going the left to right along the period and atomic size decreases while moving from the top to bottom and descending group the atomic size increases. However, on moving the diagonally from one element another element, this two effect cancel each other, and that is the atomic size diagonal of pair element remains almost constant. They show similar atomic and ionic radius, similar electronegativity, similar charge density, and polarizing power. Lanthanide contraction, the steady decrease in the size of atoms and ions elements with increasing atomic number from lanthanum to lutetium. Periodicity of elements, when increasing the atomic numbers, the properties of elements are also repeated after certain intervals due to similar electronic configuration. Cause of periodicity due to similar outer electronic configuration after certain intervals, atomic size, covalent radii. The atomic size generally decreases from left to right and increases top to bottom. Variation of covalent radii in a period. Increase in atomic number, the magnitude of nuclear charge increases while the corresponding addition of electron takes place in the same principal quantum cell, so that higher nuclear charge pulls electrons more strongly toward the nucleus. As a result, decreases the size. See lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, atomic size decreases. Variation of covalent radii in a group, the size of atom increases from the top to bottom, descending the group. In the moving down, the atomic number increases as well as the number of cells also added, so that the size of atom increases in moving from top to bottom in groups. So lithium, sodium, potassium, rubidium, cerium, atomic size increases. Ionic radii increases in moving from top to bottom in a group and decreases from left to right, variation in group. The ionic radius increases with increase in atomic number within a group. Since the atomic size increases, the ionic radius also increases. Variation in Fourier size of elements decreases along the period, so that ionic radii also decreases along the period from left to right. Ionization energy, ionization potential, it is defined as the amount of energy required to remove electron from the isolated gas system. See, sodium have the 11 electrons and the one electron is ejected. The required energy to eject this electron is called the ionization energy. This is the first ionization energy, and these successive electrons can be removed by supplying the energy. Such type of energy is called successive ionization energy. In removing the electrons, the nuclear charge is same, but number of electrons decreases. So the successive ionization energy remains in the following order: ionization is third and second and first and so on. Factors that affect ionization energy: atomic size, larger the size, the electron is the far from the nucleus and easier to remove the electron. Nuclear charge, higher the nuclear charge, difficult to remove electron from an isolated gaseous atom. Number of electrons in the inner cell, the larger the number of electrons in the inner cell, the smaller the ionization energy. Penetration effect or effect of sp electrons from the same energy cell as electrons around the nucleus have greater probability of coming closer to the nucleus, and PDF electrons of the same SPDF closer to the nucleus. Electronic configuration: certain electronic configurations are more stable than others. If half-fill and full-fill orbitals, the ionization is the higher than the expected. Also, the octet configuration is the higher than expected. Variation of ionization energy: variation in group. Ionization energy decreases going down the top in the group. The nuclear charge increases, gradually increase atomic size, increasing in the number of electrons. Variation along the period. In general, ionization energy increases as we move a period from left to right due to atomic size decreases and nuclear charge increases. D block contraction: the substantial decrease in the first ionization potential, aluminum and gallium not observed, and sodium, potassium, magnesium, and calcium. It has the 10d electrons in penultimate cell, which are less effective in the shielding the nuclear charge. The poor shielding of nuclear charge by d electrons causes strong attraction between the nucleus and outer electrons, causing the contraction of size of the gallium. This gallium is smaller due to d block contraction, and ionization energy of gallium is almost equal to aluminum. Ionization of the transition element is reasonably constant. The increased nuclear charge would attract the outer electron cloud with greater force, and hence ionization energy is expected to increase from the one element to the next transition series. However, as we electrons is added to n-1, the soft shell at this element, and then outer electrons are shielded or more. The effect of increasing nuclear charge is opposed by the additional shielding effect of nuclear provided by extra d electrons. Consequently, the ionization energy are nearly same as the first ionization energy transient in its constant. Electron affinity: the release of energy by adding electron is called electron affinity. See chlorine, one electron added in chloride. The energy is released, that the energy is called electron affinity. Factors that affect electron affinity: nuclear charge, atomic size. Increase in nuclear charge also increase electron affinity. Smaller the size of atom, higher is the electron affinity. Electronic configuration: atoms having the stable electronic configuration do not show much tendency to add extra electron and have either zero or very low electron affinity. Variation of electron affinity: electron affinity decreases in going from top to bottom in a group and increases in going from left to right across a period. Electronegativity: the property of atom to attract electron itself is called electronegativity. Pauling approach, electronegativity. Mulliken's approach, Ulrich and Loco approach. Factors influence electronegativity: charge on atom. Higher the positive oxidation state of atom is series, and greater would be the electronegativity power, and hence greater would be its electronegativity. Types of hybridization: ionization and electron affinity. According to Mulliken's, electronegativity is automatic mean of ionization energy and electron affinity. Hence, higher the ionization energy and electron affinity, higher is the electronegativity. Effective nuclear charge: higher effective nuclear charge, higher is the attracting power of the electron. Hence, higher the value of electronegativity. Variation of electronegativity in the periodic table. Effective nuclear charge, the magnitude of nuclear charge, which is felt by the value electron called effective nuclear charge, denoted by Z effective. Z minus sigma. Z is number of charge, that is atomic number. Sigma, shielding constant, which is measured by shielding effect caused by intervening electrons. Slater rules for calculation of sigma and Z effective. The value of sigma for an electron residing in ns or in the NP orbitals of the end shell of the atom or an ion is the sum of the Planck contribution. Each of the remaining electron in the end shell make the contribution of 0.35 to the value of sigma. Each of the electron in n-1 cell makes contribution of 0.85, n cell 0.35, n-1 0.85. Each of the electrons next to inner cells contribution 1, 0.35, 0.85 in 1. Zero value of sigma for the one electron present in the ns orbital of the valency cell. Sigma for 1 is contributed 0.3430. Zero value sigma for one electron present in the ns. Sigma for the electrons residing the 0.35 and 0.85 and 1. Okay, radius ratio rule. The ratio of radius cation to the anion of an ionic compounds is called radius ratio rule. Radius ratio, radius of cation over radius of anion, that is R plus over R minus. Determination of structure of ionic compounds by using the radius ratio of ions is called radius ratio rule. Let us take an ionic compounds, metal plus halide X minus, in the whose coordination of metal plus 3 ions is the 3 ion surrounded by the 3 halide ions. That is 3 possible arrangement for coordination number. 3 are there are coordination number 3 are given below. From the radius ratio, we can predict coordination number and structure of ionic crystal. Among the crystal, the coordination number are 3, 4, 6, and 8 are common. The corresponding limiting radius ratio values for these coordination numbers are given below. Okay, the limiting radius ratio 0.1552 to 0.225, coordination number 3, say planar, example boron oxide, uh, greater than 0.155, coordination number 2, triangular linear, 0.225 to 0.414, coordination number 4, tetrahedral, zinc sulfide, zinc blende, 0.414 to 0.732, coordination number 6, octahedral, sodium chloride, 0.72 to 0.998, body center, cesium chloride. The shape of crystal predicted from ionic radii of cation and anion. The radius ratio is rarely 1, and in such case, coordination number is 12. The radius ratio is predicted by the two factors. The ions of same charge avoid the coming in contact with each others. The ions of the opposite charge try to get as close together as possible so that interaction of the same charges are minimized. The radius ratio rule is applicable to the coordination numbers of cations, and the idea is to check how many anions can be accommodated around the cation, and coordination number of anion not need to be the same. Limitation of radius ratio rule, it is useful only to gauge the coordination number of a cation and not anion. It is only applied for AB type crystals satisfactorily but not crystals of A to B or AB to type. High coordination number like the real predicted by this rule does not occur in practice. This rule applicable only to crystals made of and that too only when ionic radii are known correctly. To understand ionic crystal structures, it is essential to consider not only immediate environment of one ion, but also the infinite three-dimensional character of the structure, which is ignored by Redis ratio. Theoretical calculation of lattice energy, the amount of energy released when 1 mole of ionic compound is formed from cation in an ion in gaseous state is called lattice energy. It also defines the amount of energy required to break 1 mole of ionic compounds into cations and anions in gaseous state. Bond-Land equation. The Bond-Land equation is the means calculating the lattice energy of crystalline ionic compound theoretically. In this method, the ions are treated as a point charge. According to Coulomb's law, the force of attraction between oppositely charged ions is given by capital Q1 Q2 R squared. So Q1 charge on the ion, Q2 charge on anion are distance between cation and anion. Now, if one of the ion is moved under the influence of electrostatic attraction by the distance of dr, the work done in this process given by F Q1 Q2 R squared dr. Integrating above expression from infinity to R, total work done infinity to R Q1 Q2 R squared dr. So infinity to R Q1 Q2 R minus 2 dr. So again solving Q1 Q2 minus 2 plus 1 R2 minus 1 R infinity. Again solving we get our total work done minus Q1 Q2 over R. Total work done is called electrostatic energy or attractive energy since Q1 Z plus E, Q2 Z minus E. So the electrostatic energy between two ions of opposite charge is given as E equal to minus Z plus Z minus square R. Attractive energy Z plus Z are the charge in the positive and negative ions respectively. Electronic charge are interionic distance. Total attractive energy depends on number of ions and the geometry of ionic compounds. Hence, for 1 mole of ionic compound, the equation force should be multiplied by two constants, one which represents the number of ions in 1 mole of the ionic compounds, that is Avogadro's number, and another which represents the geometry of ionic compounds, Mendeleev constant. So equation 1 can be written as attractive force A equal to minus N AZ plus Z minus square over R. Equation 2. N naught is Avogadro's constant 6.023 10 to the power 23. A Mendeleev constant. Value of H depends on the crystal geometry. The value of Mendeleev constant depends on the geometry of the ionic compounds. All ionic compounds which belong to the particular crystals structure have particular A value. And the value of A for different crystal structure has been calculated theoretically. When the positively charged ions comes together to form a crystal lattice, it is not only the attractive force that exists, but there is also a repulsive force among them. Such repulsive force arises from the electronic and internuclear repulsion of two ions. Such a repulsion is expected to increase with decreasing interionic distance r. According to Bohr and Landy, the repulsive force is given by ER B over Rn, where B a constant called bond coefficient, which depends on the coordination number, and a constant called bond exponent, typically between 5 and 12, often 9 for alkali halides. The total energy of crystal lattice is the sum of the attractive force and repulsive force, so equal to A plus ER. The total energy is called lattice energy that hold ions in crystal, hence lattice energy, attractive force plus repulsive force. It is possible to evaluate the coefficient B of the distance or attractive and repulsive force of positively charged ions are exactly balanced. The distance called equilibrium distance are not in equilibrium distance. So d over dr equals 0. Now differentiating question 3 with respect to R naught, we get and solving b equal to substituting the b in the equation 3 and we get so the equation 4 is called Boolean equation and its I unit this equation can be written as equation 5 epsilon permittivity of vacuum. Question 4 is called Boolean equation which is used to calculate lattice energy of ionic compounds. Consequence of Boolean equation, Madeline constant, charge and ion, interionic distance. Experimental calculus of lattice energy Born-Haber cycle. Let us take formation of 1 mole of metal plus and X ions from metal and X to gas. Formation of metal X by two different ways are shown in the Born-Haber cycle. C metal and sublimation, ionization energy, and the dissociation and electron affinity and the lattice energy. Different types of Born-Haber cycles. The nature of bond formed between the two atoms depends on the electronegativity difference. If the electronegativity difference between the atoms is low and predominantly covalent compounds, so bond is formed. If the electronegativity difference is high, then the predominantly ionic compounds will be formed. It means that percentage ionic characters are divided into three categories. The electronic difference of atoms is greater than 1.7, the bond will be the predominantly ionic. If the electronic difference is less than 1.7, predominantly covalent. If the electronic difference of atoms is equal to 7, then 50% ionic and 50% covalent. Polarization. When ions approach each other closely, the cation attracts the electron cloud, the anion, and simultaneously the nucleus of the anion repels the cation. These two forces produce deformation of the anion and spherical electron cloud of the anion becomes distorted. This above distortion of electron cloud is called polarization. If the degree of polarization is large, electrons are drawn from the negative ions towards the positive ion, resulting in the high concentration of electrons between the two nuclei and resulting in the large degree of covalent character. If the degree of polarization is quite small, then the bond remains largely ionic. Polarizability is the measure of the how easily an electron cloud is distorted by electric field. Also, we can define the polarizability is defined as the ease at with which the electron cloud of an atom or molecule is distorted and denoted by alpha. So alpha equal to mu over E epsilon and mu dipole moment epsilon electric field. Poisson's rules, a rule formulated by Poisson in 1923, are used to predict whether a chemical bond will be covalent or ionic and depends on the charge on the cation in relative size of cation in anion. See, ionic bond, covalent bond, low positive charge in ionic bond, high positive charge. In case of ionic bond, low positive charge, large cation, small anion. Covalent bond, high positive charge, small cation, large anion. Small cation favors covalency. In small cations, the positive charge is concentrated over a small area and this gives greater polarizing power of an anion. For example, barium chloride is more covalent than calcium chloride due to small size of the beryllium ion compared to calcium. Large anion favors covalency. The electron cloud in a
Large anion is diffuse or loose and can be easily distorted. Therefore, a cation can polarize a large anion more than a small anion. This would increase the covalency. Example, calcium plus is the given cation as the size of the anion increases from chloride to iodide, the polarizability increases and consequently covalent character increases from calcium chloride to calcium iodide. Large charge upon the ideal cation or anion favors covalency. The enhanced force of attraction resulting from high ion charge increases the polarization and increases the covalency. Large cation has greater polarizing power and large charge anion has high polarizability. Aluminum chloride is more covalent than sodium chloride. Aluminum plus 3 is more powerful than cyanide plus in polarizing anion chloride. When the charge on the anion is more, it has more diffuse electron cloud. This electron cloud is distorted by the cation. Barium oxide pool is more covalent than barium chloride because of oxide is the diet negative while the chloride is the uninegative. Cation with non-inert gas structure favors covalency. Cations with non-inert gas electron structure have the greater polarizing power than the cations with inert gas structure NH2 and P6, that is the 8 electrons structure cation with electronic configuration cause the least distortion than the those NH2 and P6 and the 10 configuration due to floor sealing effect of the electrons of nuclear charge. For example, melting point of sodium chloride and potassium chloride are most higher than those of the copper chloride and silver chloride. Copper chloride is more covalent and sodium chloride is more ionic due to greater polarizing power. Copper plus 2 is to 3p6 10 than the sodium plus 2 is to 2p6. Okay, crystal structure in crystallography. Crystal structure is a description of the ordered arrangement of atoms, ions, or molecules in crystalline material. Ionic compounds X-type cesium chloride, cesium and chloride are 600 uh, 69 picometer and 181 picometer respectively. Hence, limiting radius ratio is 0.938. So, coordinate number. The radius ratio of 0.933 indicates that body-centered cubic types of arrangement. One cesium ion is surrounded by the 8 chloride ions and one chloride is surrounded by the 8 cesium ions. Hence, coordination number is 8 is to S. The compounds such as cesium bromide, cesium iodide, titanium chloride, titanium bromide have the same structure with cesium chloride. Sodium chloride, the ionic radii of sodium and chloride ions are 95 picometer and 181 picometer respectively, so 0.524, 6 coordination number. The radius ratio of 0.524 indicates that the octahedral arrangement, one sodium ion is surrounded by 6 chloride and one chloride is surrounded by the 6 sodium. Therefore, coordination number is 6 is to 6. Zinc blendy, the ionic radii of zinc and sulfide are 74 picometer and 184 picometer respectively. 0.404 coordination number. 0.40 indicates that tetrahedral arrangement and clear that each of the zinc flaws is surrounded by the 4 sulfide ions and each sulfide is surrounded by the zinc ion, that is the coordination number of both zinc and sulfide ion is the 4, that is 4 is to 4 arrangement. Any compounds extra type structure of calcium fluoride. Fluoride structure is obtained when the radius ratio is 0.73 or above in calcium fluoride. Each calcium plus ion is surrounded by 8 fluoride ions, giving the body center cubic type arrangement of ions. Each fluoride ion is surrounded by the 4 calcium ions. Giving the tetrahedral arrangement of ions, the coordination number is 84. Titanium oxide rutile crystal structure. Three different forms of titanium oxide exist, namely rutile. Structure of rutile is obtained when the radius ratio between 0.41 to 0.73. This suggests that one of the ions should adopt coordinate number 6 from the formula. It is evident that another ion must coordinate number 3. Hence, the radius ratio becomes 6:3. Rutile structure titanium plus 4 ion is surrounded by 6 oxide ion, and oxide ion is surrounded by 3 titanium ion, giving the triangular arrangement. Rutile lattice point, the position of each constituent particle in a three-dimensional structure of crystal is represented by a point which is called point lattice point. Crystal defects idle crystals. There are those crystals in which all the lattice points are occupied by the corresponding ions and the interstitial space are vacant. Idle crystal exists only at 0 Kelvin temperature. Defected crystal are those crystals in which one or more lattice points are vacant and the interstitial space are occupied by ions. All crystals are defected under normal condition. Impurity defect. In this type of defect, one or more cations and anions or both are missing from the crystals and these positions are occupied by some other kinds of ions. Stoichiometric compounds, the ionic compounds in which cations and anions are present in the ratio represented by their valency are called stoichiometric compounds. These compounds follow the law of constant composition: sodium chloride, calcium chloride, aluminum chloride. Non-stoichiometric compounds, the ionic compounds in which cation and anion are not present in the ratio represented by their valency are called non-stoichiometric compounds. These compounds do not follow the law of constant: sodium chloride, ferrous oxide. Sodium chloride 0.98 plus 0.86, 0.84. Types of defects: stoichiometric defects, defects ionic compounds in which missing cations and anions do not stoichiometric rules of ionic compounds is called stoichiometric defects. Schottky defects. In these defects, ions are missing both cations and anions. Lattice point in stoichiometric ratio that is represented by valency. The missing of ions occupied by the surface of crystal. These defects arise in those ionic compounds, smaller size of cations and anions. High coordination numbers, Schottky defects, missing of cation and this missing of anion, cation, anion. Schottky defects, C, Schottky defects, anion, cation, anion, cation, anion. Frankel defects. In these defects, the ions are missing from the lattice points and occupy the interstitial space. These defects arise to those ionic compounds in which the cations are smaller than the anions. Low coordination numbers, for example, silver chloride, zinc sulfide, and silver bromide. Stability of ionic compounds decreases due to repulsion between the ions. Schottky decreases density of ionic compounds. This is the Frankel defects. Missing this cation and occupying interstitial space. Non-stoichiometric defects in ionic compounds in which the absence of cations or anions changes the ratio of ions from that required by their valency are called non-stoichiometric defects. In these defects, the ions are not present in the ratio represented by their valency. The defects arise by the following two ways. Metal deficiency defect, that is the non-metal access defects. The ionic compounds in which the number of metal ions is less than the stoichiometric ratio are said to be the metal deficiency defect. Positive ion absence defect occurs when one or more cations are missing from their normal lattice positions, creating cations vacancies. To maintain electrical neutrality, some nearby cations acquire an extra positive charge and are converted into cations with higher oxidation state. For example, iron ferrous oxide, nickel oxide, and ferrous sulfide. In this type of metal defects cause semiconductor and also called p-type of semiconductor, cation vacancy, and cation is extra positive charge. Extra interstitial ions, extra interstitial anions, and extra negative ions is present in an interstitial position, and to maintain the charge balance, a nearby cation acquire extra positive charge. However, negative ions are usually large. It would be difficult to fit them into interstitial position. No any examples of crystal containing such negative interstitial ions are known as present. Metal deficiency caused by interstitial negative ions due to interstitial cations, due to anion vacancy. Metal access defects, the off-center negative ions absent, and anion may be missing from its lattice site, creating a vacancy. This is occupied by electrons. Maintain the electrical neutrality. This type of decay is off-center, which usually crystal dart is expected to Schottky defects. The off-center metal access. Extra interstitial cations or electrons, and extra cation occupies an interstitial position in the lattice and to maintain the electrical balance. An electron is also present in this interstitial position. This is defect is called Frankel defects. Okay, theories of covalent bonding. Three types of theories of covalent bonding: valence bond theory, valence electron pair repulsion theory, molecular orbital theory. Valence bond theory, it was proposed by Hitler and London. According to valence bond theory, the covalent bond is formed by the overlapping by atomic orbitals is containing unpaired electrons. Later on, this theory was explained by Pauling and Slatin to explain the directional nature of the covalent bond and shape of the covalent molecule. Postulates of valence bond theory, a covalent bond is formed by overlapping unpaired electrons. The greater the extent of overlapping of atomic orbitals, stronger is the covalent bond is formed. That is, small orbitals form stronger bond and large orbital form weak bond. Number of covalent bond formed by an atom with other atom are equal to number of unpaired electrons present in atomic orbitals. Resonance play important role in valence bond theory. Paired electrons do not form covalent bonds, however, it can form covalent if it is made unpaired by excitation. A covalent bond is formed in the direction in which electron density are maximum. That's why covalent bond is directional in nature. Depending upon the way of the overlap, two types of covalent bond is formed, namely sigma bond and pi bond. Limitation of valence bond theory, the existence of coordinate bond is ruled out in which both electrons come from the only one atom. It does not explain the paramagnetic nature of some molecules like oxygen. It does not explain the formation of molecular ion like hydrogen and helium. Hybridization, mixing of atomic orbitals of valence shell of central atom to produce new kinds of orbitals having the equivalent energy is called hybridization, and new orbitals also called hybrid orbitals. Rules of hybridization, it is the atomic orbitals of valence shell of central atom that participate in hybridization. The atomic orbitals of participating in hybridization should have approximate same energy. Number of hybrid orbitals formed are equal to number of atomic orbitals. Hybrid orbitals always form sigma bonds and never form pi bonds. The atomic orbitals that have to form the pi bonds do not hybridization. Three types of atomic orbitals undergo hybridization: atomic orbitals containing unpaired electrons, atomic orbitals containing unpaired electrons, and paired electrons. Backend atomic orbitals, hybrid orbitals, has one larger and another lobe smaller. Only larger lobe participate in bonding. Shape of covalent molecules depends on types of hybridization involved in the central atom and lone pairs, bond pairs, that is number of hybrid orbitals formed. sp, sp2, sp3, sp3d, sp3d2, sp3dt, dsp2, and these are the types of hybridization. Sp hybridization, it involves mixing of 1s and 1p orbitals to produce sp hybrid orbitals, for example, beryllium fluoride. Shape is the linear shape of the hybrid orbitals. sp2 hybridization, combination of 1s and 2p orbitals to form three hybrid orbitals equal to energy known as sp2 hybridization, for example, boron trifluoride. The shape of boron trifluoride is the trigonal planar shape of sp2 hybrid. Sp3 hybridization, the combination of 1s and 3p orbitals to form four hybrid orbitals of equal energy known as sp3 hybridization. For example, methane C1s 3p and forms tetrahedral shape of the sp3 hybrid orbital. sp3d hybridization involves the mixing of 1s orbital, 3p orbital, and 1d orbitals to form five sp3d hybridized orbitals of equal energy. They have trigonal bipyramidal geometry. See, and this is the trigonal bipyramidal geometry. sp3d2 hybridization, the combination of 1s and 3p orbitals to form six hybrid orbitals of equal energy is known as sp3d2 hybridization. For example, sulfur hexafluoride molecule. sp3d3, the combination of 1s, 3p, and 3d orbitals to form 7 hybrid orbitals of equal energy is known as the sp3d3 hybridization. Example, iodine heptafluoride molecule. dsp2 hybridization, dsp2 type of hybridization is seen especially in case of transition metal ions. The orbitals involved in this type of hybridization are dx square, y square, and 2p orbitals to 4 dsp2 hybrid orbitals adopt square planar geometry. See, this is the dsp2 hybrid orbitals square planar geometry. dsp3 hybridization, one is trippy and the orbitals same atom having nearly same energy mix with each other form 4 dsp3 hybrid orbitals. Geometry is linear. Valence shell electron pair repulsion theory. In polyatomic molecules, the electron pairs, lone pairs, and bond pairs present on the valence shell of central atom exert mutual repulsion among themselves. They tend to far away from each other as far as possible. In this way, due to the repulsion they experience minimum repulsion and hence attain maximum stability. This is the basic concept of valence shell electron pair theory. In order to explain decrease in bond angles, they propose following postulates. Postulates of valence shell electron pair repulsion theory: if the central atom of the molecule possesses only bond pair of electrons, then shape of molecule is regular. If the central atom of molecule possesses both lone pairs of electrons and bond pairs, the shape of molecules becomes irregular. Bond angles in molecule decreases due to repulsion between lone pairs and bond pairs. The extent of repulsion between the different electrons pair decreases in order: lone pairs repulsion, lone pair bond pair repulsion, and bond pair repulsion. Example of involving the valence shell electron pair repulsion theory: boron trifluoride, the sp2 lone pair 0, number of pair 3, so it is the regular shape. Boron tetrafluoride, lone pair 0, and shape tetrahedral. Boron pentachloride, sp3d1 hybridization, number of bond pairs, lone pairs 0, trigonal pyramidal. Ammonia, number of lone pairs, number of bond pairs 3. So, shape trigonal pyramidal spatial orientation of electrons pairs tetrahedral, in which one position is occupied by the lone pair, bond angle 109.5 to 107 degree, 48 minutes. Water, the number of lone pairs 2, and the geometry of water molecules is the tetrahedral, but actual shape is V-shape, angular or bent. Chlorine trifluoride, number of lone pairs 2, and orientation of 5 electron pairs, triangular bipyramidal, in which 2 lone pairs occupy equatorial plane, but actual shape is T-shaped. Sulfur tetrafluoride, lone pairs 1, the triangular bipyramidal, but actual shape is linear. Similarly, genuine tetrafluoride, number of lone pairs 2, shape is octahedral. Iron pentafluoride, lone pairs 1, the square pyramid, sulfur hexafluoride, lone pairs 0, and distorted octahedral. Xenon fluoride, shape is linear. Iodine heptafluoride, phosphorus pentachloride, Molecular orbital theory. According to the molecular orbital theory, all the atomic orbitals of atoms participating in the formation of molecules mixing up to the form of new kinds of orbitals called molecular orbital. So molecular orbitals are responsible for the formation of molecules. It means atom consists of atomic orbitals, but molecule consists of molecular orbitals. Number of molecular orbitals form equal to number of atomic orbitals mix. The molecular orbitals assumes that atomic orbitals from the atoms combine to produce new set of orbitals called molecular orbitals. Such molecular orbitals are described by wave functions according to quantum mechanics. Basic principles of molecular orbital theory. When the nuclei of two atoms come close each other, their atomic orbitals interact, leading to formation of molecular orbitals. The atomic orbitals of atoms in a molecule completely lose their identity after formation of molecular orbitals. Each molecular orbital is described by a wave function known as the molecular orbitals wave functions. The molecular orbital wave function psi is shows that psi square represents the probability or density or electron charge density. Is a molecular orbital wave function psi is associated with a set of quantum numbers which determine the energy and the shape of molecular orbital. Electron fills the molecular orbitals in the same way as they fill the atomic orbitals, following the of principle, Pauli's exclusion principle, and Hund's rule maximum multiplicity. Each electron in a molecular orbital belongs to all the nuclei present in molecule. Each electron moving in a molecular orbitals has spin plus half and minus half. Linear combination of atomic orbitals principle of molecular orbitals theory. The wave functions describing the molecular orbitals are obtained by a method called linear combination of atomic orbitals. Molecular orbitals are formed by the linear combination of atomic orbitals. Linear combination of two atomic orbitals wave functions are brought about by the addition and subtraction overlap of atomic orbitals. Let psi and psi b are the wave functions of two atoms A and B, and psi molecular orbital be the wave function of the molecule AB. When two atomic orbitals overlap, the new wave function psi AB and molecular orbital psi molecular is formed and can be obtained by the linear combination of atomic orbitals psi A and psi B. So psi AB equal to n C1 psi A plus C2 psi B. N is the normalizing constant, which ensures that the probability of finding electrons in the whole space C1 and C2 are the constant which gives the minimum energy for psi AB. The probability or density for the combination of two atoms is given by the square of the wave functions. So psi square AB equal to n C1 psi A plus C2 psi B square. So C1 square psi A plus C2 C1 C2 psi A psi B and C2 square to psi B square. If n is 1 2 C1 square A probably finding A C1 square and C2 square is probably finding in B. And 2C1 C2 2C1 To C1, C2, psi A, psi B, the overlap of the two atomic orbitals. The larger the 2C1, C2, psi A, psi B, it is the stronger is the bond in between A and B. There is the higher electron density and the internuclear region, and beyond is the stronger. There will be the two molecules orbital as the result of two types of combination as given. So psi B molecular is the psi A plus psi B. So that is the psi bonding, and psi star, that is the anti-bonding molecular psi A minus psi B. The concentric represent the formation of bonding molecular orbitals. It is the form by the addition overlap of atomic orbitals, that is overlap of the atomic orbitals having the same sign. Equation 4 represents the formation of antibonding molecular orbitals. It is formed by the subtraction overlap of atomic orbitals, that is overlap atomic orbitals having opposite sign. Pieces of bonding molecular orbitals, it poses lower energy than atomic orbitals from which it is formed. It has higher electron density than two nuclei and stable. It is formed by the combining atomic orbitals having the same sign, but magnitude of psi b is always bigger than psi a minus psi b. Our electrons in bonding psi molecular orbital contributes to attraction between two atoms. Features of antibonding molecular orbitals, it possesses higher energy than the atomic orbitals from which it is formed. The probability of finding the electron in between the nuclei is negligible. It is formed by the lobes of the combining atomic orbitals have opposite sign. Psi star is numerically smaller than psi A or psi B. Every electron in an antibonding molecular orbitals contributes to repulsion between two atoms, that is atomic orbital and sigma star. Rules for linear combination of atomic orbitals. The combining atomic orbitals should have roughly the same energy. The overlapping orbitals must approach each other closely enough for considerable overlap to form molecular orbitals effectively. For producing bonding and antibonding molecular orbitals, either the symmetry of two atomic orbitals must remain unchanged when rotated about the internuclear axis, or both the atomic orbitals must change the symmetry in the identical manner. Diagrammatic representations of formation of molecular orbitals and atomic orbitals: SS overlap, subtraction overlap, SPX overlap, addition overlap, subtraction overlap, PY overlap, addition, and PX, same sign, subtraction. Similarly, PZ overlap like PY overlap, and also it pi bonding and pi star molecular orbitals. Condition of LCO: in order to form molecular orbitals, the atomic orbitals should flow the flowing condition. The atomic orbitals participating in the formation of atomic orbitals should have approximate same energy. The atomic orbitals should overlap is order as well as possible is given maximum overlap of atomic orbitals. The atomic orbitals should have same symmetry along the molecular axis, and this is also called symmetric condition for linear combination atomic orbitals. So 1s overlap, 2s, then 2p overlap, by 2pz by antibonding, pi bonding. Similarly, y by antibonding, pi bonding, and pi bonding and pi antibonding. X to px. Relative energy of molecular orbitals up to 14 electrons. One is sigma bonding and one is sigma antibonding. Two is sigma bonding and two is sigma antibonding. Pi to py and pi to pz and pi to px. Then pi to py, pi to py antibonding and pi sigma star antibonding to X. In case of heavier tones, then from 14, sigma 1 is and sigma 1 is antibonding, 2 is bonding, sigma 2 is antibonding, sigma 2 by px, and pi to py, pi to pz, and pi antibonding to py, pi into 2 pz, sigma 2 px. For example, molecular orbital of oxygen, say oxygen at electrons, sigma 1 is bonding, sigma 1 is uh, antibonding, sigma 2 is bonding, sigma 2 is antibonding, and pi to px bonding, and sorry, sigma 2 px bonding, sigma 2 py, and sigma 2 pz bonding. So electrons 2, 4, 6, 8, 10, 12, 14. We have this at 16 electrons. So pi antibonding to Py and pi antibonding to Pz. So similarly, O2 plus and O2 minus. Molecular orbital of the nitric oxide in case of nitrogen atom and the oxygen atoms. Sigma 1 is and bonding, sigma 1 is anti-bonding, sigma 2 is bonding, sigma 2 is anti-bonding, sigma 2 px bonding, and pi 2 py and pi 2 pz bonding, and pi star to py anti-bonding, pi star 0 to pz anti-bonding, sigma star to px anti-bonding, 0 anti-bonding. Similarly, carbon monoxide, boron. Difference between valence bond theory and molecular orbital theory. According to valence bond theory, atomic orbitals do not lose their identity in their molecule. According to molecular orbital, the atomic orbitals lose their identity and forms new kinds of orbitals called molecular orbitals. Only valence shell atomic orbitals participate in bonding. All the atomic orbitals of atoms participate in bonding. In atomic orbitals, the electrons are influenced by single nucleus, that is the monocentric. In the molecular orbitals, the electrons are influenced by atom or molecule, that is polycentric. It cannot explain the paramagnetic property of molecule of oxygen. It can explain the paramagnetic properties of molecules. It does not explain the formation of molecular ion like helium plus. It can explain the formation of their molecules. It do not consider fractional bond order. It considers bond order. Resonance played important role in BBT. Resonance is no role in the molecular orbital theory. Hard soft acid base SSB principle. It states that soft acid prefer to form bonding with soft base and hard acid prefer to bonding with hard base. This means that hard acid and base are from stable complexes. Similarly, soft acid and base also from the more stable complex. Bonding between hard and soft acid are not stable, therefore this principle is very useful predicting the relative stability of complex. Conjugate acid pair. When acid loses proton, then residual part of it have tendency to accept the proton again. Factors affecting the relative strength of acid and base effect of solvent. The solvent which exhibit their acidic or basic property and in solution, the solvent plays very important role in the acidic or basic strength of such substances. Effect of solvent on the strength of acids, strength of acid in water, that is leveling effect. The tendency of water to equalize the strength of many acids of base stimulates the leveling effect and hence what is called leveling solvent. In aqueous solution, the extent of dissociation of acid depends upon the tendency of water molecules to accept S plus ion on the basic strength of water. Water acts as a good base towards all common strong acids like hydrochloric acid, sulfuric acid. They are almost completely dissociated in aqueous solution such that all of them appear equally strong in aqueous solution. Strength of acid in acetic acid in differentiating effect. The solvent in which strong acid ionize to different extents so that relative strength of acids can be measured are known as differentiating solvents. For example, acetic acid is a differentiating solvent and acetic acid is weak acid and it also behaves as also behaves some extent that is acid proton, nitric acid and acetic acid, the acid and the base. Therefore, even strong acid feebly ionized in this solvent. And that is a strong acid acts with weak acid in acetic acid. Effect of solvent on the strength of base. In aqueous solution, the relative strength of base depends on the tendency of water to donate S plus ion. That is on the acidic strength of the solvent. Water acts as the weak acid, that is, acts as the differentiating solvent for bases. On the other hand, aniline acts as the weak base. Water appears to be strong base when dissolved in acetic acid as solvent. Effect of substitution on the relative strength of acid and base. The relative strength of acid and base is greatly influenced by the nature of substitution, that is electron releasing and electron withdrawing group and the number of present on them. Effects of electron releasing group on the strength of basic electron releasing group increases the electron density between hydrogen donor atom and which is decreases the polarity of the bond. This hinders the dissociation of hydrogen S plus and acidic strength decreases. For example, acetic acid is stronger than the propanolic acid and propanolic acid is stronger than the methyl propanolic acid. Number of electron releasing group increases, electron density between hydroxide bond increases, strength of hydroxide increases. Polarity of waste decreases, rate of dissociation of hydrogen plus decreases, acidic strength decreases. Effect of electron releasing group on acidic strand. It is considered the comparison of acidic strand of acidic, fluoroacidic, and acid and difluoroacetic acid. The electron releasing group decreases. Number of chlorine is increases. Number of electron withdrawing groups increases. Now electron density between hydroxide bond decreases. Strength of Weiss bond decreases. Polarity of Weiss bond increases. Tendency of hydrogen dissociate SS plus increases. Acidic strength increases. Effect of electron releasing group on strength of Lewis acid, Lewis base, sorry. Let us examine the strength of flying Lewis base, basic strength. Number of electron releasing group increases. Electron density of nitrogen atom increases. Tendency to donate the lone pair increases. Basic strength increases. Effect of electron withdrawing group on the strength of Lewis base. Let us examine the strength of flying Lewis base. Number of electron withdrawing group increases. Electron density of nitrogen atom decreases. Tendency to donate the lone pair decreases. Basic strength of Lewis base decreases. Steric effect. This is trimethylamine should be strongest base, but it is the weakest in the above series due to steric effect. This the electron donating capacity of nitrogen atom is hindered due to presence of three methyl groups, and hence basic strength is very poor. Effect of electronegativity. Strength of acid increases if the electronegativity of central atom increases. Let us examine the relative acidic strength of the molecule methane, ammonia, water, and hydrogen fluoride on the basis electronegativity. Electronegativity of halogen atoms increases. Ability to withdraw the electron pair increases. Polarity of X halogen X bond decreases. Tendency to dissociate S plus increases. Acidic strength increases. Of the above molecules, hydrogen is covalently bonded to carbon, nitrogen, oxygen, fluorine, whose electronegativity increases in the order. As the electronegativity of central atom increases and XS bond becomes more polar, more ionic, and hence tendency to dissociate hydrogen as S plus increases from methane to hydrogen fluoride, so that acidic strength is so on. However, this rule is not valid for halogen acids, so relative acidic strength cannot explain on the basis of electronegativity because it gives the opposite order. Atomic size of halogen atoms increases. Strength of hydrogen halogen bond decreases. Rate of dissociation of hydrogen S plus increases, so that acidic strength increases. Oxidation state, the relative strength of acids on element is determined by their oxidation states. Number of oxygen atoms bonded to chlorine increases, electron withdrawing effect increases. Electron density between oxygen-hydrogen bond decreases. Polarity of oxygen-hydrogen bond increases. Tendency of hydrogen to dissociate as S plus ion increases. Acidic strength increases. So acidic strength is in this order. However, a series of oxyacids containing the different halogen atoms but same number of oxygen atom, that is the same oxidation state, their relative acidic strength is determined by electronegativity, that is the acidic strength decreases if the electronegativity of halogen atoms decreases. Electronegativity of halogen atoms decreases and electron withdrawing effect decreases. Electron density between oxygen-hydrogen bond increases. So strength of oxygen-hydrogen bond increases. Tendency of hydrogen to dissociate as S plus decreases, acidic strength decreases. So acidic strength in this order. Nature of bonding. In boron trifluoride, though the partial positive charge on boron atom is more due to the high electronegativity of fluorine, the tendency to accept a lone pair is reduced because of ability of fluorine atoms to donate their own lone pair to the anti-boron orbitals forming p5 back bonding. Fluorine forms the strongest backbone due to the effect of overlap between 2p and 2p fluorine and 2p boron orbitals, so the electron deficiency of boron gets compensated and the Lewis acidic character decreases. But as the size of the orbital increases, the extent of back bonding decreases. This is due to the ineffective overlap, as in case of 3p and 4p orbitals of chloride and bromide respectively, with that of the 2p orbitals of boron. So the extent of back bonding boron trifluoride and boron trichloride, bromide, and hence the Lewis acidity in this order. Size of p orbital on phosphorus p orbital on the halogen atom increases. Extent of p5 overlap between the boron and halogen atom increases. Electron deficiency of boron atom increases as the extent increases. In case of boron trifluoride, p5 back bonding is effective but not effective in boron iodide. Application of common ion effect. Common ion is the most applied in salt analysis, that is the qualitative analysis of basic radicals in group separation. When a strong analyte having the common ion is added to a solution, dissociation of weak electrolyte suppressed to the desired extent. Consequently, conditions are created when one cation is selectively precipitated but other remains dissolved in solution. Precipitation of group first metal ions in basic radicals. Group first metal ions basic radicals are mercury, silver, lead, and when added with hydrochloric acid, PPT precipitated as chlorides. Solubility product of chloride is very low, and the comparison of chlorides of basic radicals of other groups, these low solubility products are easily exceeded by the ionic products. Hence, metal ions easily precipitate on addition of dilute hydrochloric acid. Precipitation of group second metal ions, mercury second, copper second, stannum second, cadmium second, arsenic second, and so on. Added the sulfuric hydrogen sulfide. Precipitate as sulfide. When hydrogen sulfide is only passed through the solution, the ionic product of corresponding metal ions and sulfide ions not only exceed the solubility of product of group third B, hence acidified with an hydrochloric acid, hydrogen sulfide is passed through the solution. Hydrochloric acid is a strong electrolyte and produces large number of S plus ions. Hydrogen sulfide is weak electrolyte which produces small number of hydrogen ion in solution. Due to common ion effect, the dissociation of hydrogen sulfide is suppressed. At this time, the ionic product is just sufficient to exceed the solubility product of group second metals, but not the group third metals. So that metal ions of group second are precipitated as the sulfide, but metal ions group third B are not precipitate, even they are present in solution. Precipitation of group 30 metal ions, ferrous, aluminum, and chromium hydroxides. Group 30 metal hydroxides, if when the ammonium hydroxide is added, the ionic product of corresponding metal ion hydroxide not only succeeds group 30 but also succeeds the soluble product of 30. In order to avoid the precipitation of 30 along the 30 ammonium hydroxide, presence of ammonium chloride strong electrolyte ion produced large number of ammonium ion solutions. However, ammonium hydroxide weak electrolyte which produce least number of ammonia. Dissociation of ammonium hydroxide suppressed very much due to common ion effect. In this condition, ionic product is just sufficient. Group IV metal ions carbonates. Only ammonium carbonate is added to the solution. The ionic product of ions may also exceed the solubility product of magnesium carbonate, may also precipitate along with the group IV metal ions. In order to avoid the precipitation of magnesium carbonate along with group IV, ammonium chloride is added before the addition of ammonium carbonate. Degree of dissociation ammonium carbonate is suppressed very much in solution due to common ion effect. At this condition, the ionic product of group IV metal carbonate is just sufficient to exceed their solubility product. Since the solid product of magnesium carbonate is the high, it is not exceeded by its ionic product, so that group IV metal ion precipitate but not magnesium. Gravimetric analysis, this method concept B determines precipitate from the solution by addition of suitable precipitation agent. Volumetric analysis, quantitative chemical analysis carried out by determining the volume accurately, known as the concentration, which is required to react with quantitatively measured volume of solution substance determined. Analyte, analyte is substance in a sample that is to be investigated. A general opinion of chemists adopted by the structure is the central concept. Properties of given substance depend on the number and nature of its constituent atoms and their mode. After having defined the concept of structure, we proceed to discuss correlation structure and properties, with special emphasis on the special features, structure, and properties. Atomic orbitals We have already discussed hybridization. Polar covalent bond, the covalent bond in which the one atom has greater attraction for the electrons than the other atoms. If the relative attraction is great enough, the bond is ionic. Inductive effect is occurs when a molecules experience an uneven distribution of bonding electrons, leading to formation of permanent dipole in that molecule. This redistribution of electrons is caused due to electron donating or electron withdrawing in the molecule. Positive inductive effect is seen in atoms or groups that have tendency to give electrons. It describes the ability of substitution or functional group to donate electron density to a neighboring atom through the sigma pulse. Alkyl groups are well-known instances of groups that donate electrons such as methyl, ethyl. The observation of positive inductive effect occurs upon the attachment of these groups to the carbon atom. Negative inductive effect can be observed in electron withdrawing atoms or groups that tends to withdraw electrons density from neighboring atoms through sigma bonds. Common example of electronegative atoms: oxygen, fluorine, chlorine, bromine. The observation of negative inductive effect occurs upon the attachment of these groups to a carbon atom. It can influence various chemical properties and reactions of the atom. Order of inductive effect. The order of inductive effect is determined by the group's ability to donate or withdraw electron density from molecule. Higher electronegativity electron withdrawing groups have the stronger inductive impact. Lower electronegativity electron donating groups have lesser inductive effect. The order of inductive effect is given below: halogens, electronegative elements. Inductive effect on acidity and basicity. Inductive effect can be used to determine the acidity and basicity of various compounds. Electron withdrawing compounds become more acidic, and when substitution use sigma bonds to remove molecules electron density from away from it. The reason for this is that the reduction in the electron density facilitates the donation of proton, halogens, carbonyl groups, nitrogen groups. A few examples of electron withdrawing groups. Electron donating groups becomes more basic when substituted by sigma bonds containing electron density. This is due to the fact that the molecule may more easily take up proton when electrons are available. Alkyl groups, hydroxyl groups, amino groups are few examples of electron donating group. Plus, in the positive inductive effect will decrease the acidity of compound and enhance the acidity of compounds. Difference between inductive effect and mesomeric effect: electron density transferred by sigma bonds. Electron density delocalized by lone pairs or pi bonds. It is effective up to 3 carbon atoms. It is applicable along the length of conjugated system. It operates the saturated and unsaturated compounds. It operates unsaturated and conjugated compounds. Inductive effect was resonance effect. Inductive effect is caused due to transmission of electrical charge between atoms in a molecule. Resonance effect caused due to transmission of electron pairs between atoms in a molecule. It occurs due to polarization of bonds. It occurs due to presence of sigma and double bonds. It is affected by electronegativity of the atoms. It's affected by arrangement of double bonds. inductive effect, and electromagnetic effect. It involves the displacement of electron along the sigma bonds. It involves displacement of electron along the pi bonds. It is permanent temporary. Partial charge separation takes place. Complete charge separation takes place. It changes the molecule's total electron density. It only modifies the electron density at the multiple bond site. Attacking reagent is not required. Attacking reagent is required. Hydrogen bonding. Okay. Chemical formula. It is the combination of symbols caused to express the chemical components. Chemical components of substance, for example, C6H12O6. Empirical formula, the chemical formula that expresses the proportion of the elements present in the substance. So, for example, one carbon is the proper ratio of the hydrogen is the 2 and the 1 oxygen. It's the empirical formula of the glucose. Molecular formula, a chemical formula that expressing the number of each element present in substance without indicating how they are linked. A spatial formula, spherical formula, chemical formula giving the number of atoms is element present in the molecule substance. Which atom is linked with which? This type of linkage involve the relative position of the atoms is in space. This is the bone between the plane away from the observer, bone above the plane toward the observer. Fisher projection formula of plane of projection or projection formula of three-dimensional molecular model obtained by drawing the main chain in the vertical arrangement and other groups on the other side of that chain so that bonds vertically are considered to be below or behind the projection plane and horizontal bonds above or in front of that plane. This is the Fisher projection formula. Bone above the plane toward the observer and bone between the plane away from observer. So Fisher projection formula is the convention used to depict a stereochemical formula without destroying the stereochemical information, that is the absolute configuration at chiral center. As the numbers of chiral carbon increases, it becomes difficult to draw these structures in perspective 3 dimensions. Stereochemical differences becomes very difficult to pick up. See, this is the Fisher projection formula. Newman projection formula. Newman projection are a way of drawing conformation. The front carbon atom is represented by the 3 lines, 3 bonds coming together in a Y shape. The back carbon is represented by a circle with 3 bonds pointing out from it, and these bonds again come together in the form of the incomplete Y shape. The molecules viewed along the axis of the given below. See, this is the perspective of drawing of the ethane. The front carbon is in the center with the Y form, and this back carbon is the incomplete Y in the circle. This is the Newman projection formula. Sahor's formula. A formula looks like a carpenter's Sahor's, and so it's called Sahor's. It's similar to that Newman projection formula, but in case of Newman projection, carbon bone is hidden. This is another alternative to representation by the Weiss and Dash model. The name of this projection comes from the similarity that the drawings of the molecules show with the Carpenter's Sahor's. This way, the representing molecules has the okay, the way of representing molecules has the pro of observing the bond formed by the carbons in organic molecules and allows the 3D perspective of the molecules drawn on paper to be obtained. See, this is the Newman, is the sawhorse. This is the back carbon, and this is the front carbon. Chiral center is defined as atom, a molecule that is bonded four different chemical species and already optical isomerism. For example, central carbon in serine is chiral carbon, the amino group, and the hydrogen are important carbon. See, 1, 2, 3, 4 different types of the substance in this carbon. Conformation, the different structures which is resolved by rotation about single bond is called conformation. The different arrangement of atoms which reflect its order, carbon sigma bond, rotation called conformation. The arrangement of atoms in space molecules define constitution with regard to arrangement that differ only after rotation about one or more single bond is called conformation. Absolute configuration for chiral molecule in the stereochemistry 3D orientation. Relative configuration refers to the qualitative configuration that relative configuration relate the configuration of one compound with other. Conformation of butane. In butane, there are the three carbon-carbon bond possible for rotation among these three carbon-carbon bonds between C2 and C3 is considered as the bond having the center of gravity. It has flowing different conformations. Say NT 3.4 kilocalorie and gauze. This is the fully eclipse 4.4 to 6.1. Partial eclipse 3.4, full eclipse 4.4 to 6.1. Static strain repels interaction between methyl groups, that is the bulky groups of neighboring groups. Torsional strain destabilization of eclipse conference lead to staggered condition. The energy required to rotate molecule around the carbon-carbon bond is torsional strain. Static strain is the repulsion between the two atoms or groups of atoms when the distance between them is decreased. Torsional strain is the repulsion that arises between the atoms or groups of atoms when molecules rotate around the sigma bond. Cannot be lessened by rotating the molecule around the sigma bond.
can be lessened by rotating the molecule around the sigma bond. Occurs when the distance between the bulky groups of molecules decrease. Occurs when the bond electrons pass by each order when the molecule rotating. Preparation of alkane from Grignard reagent. Any class of reagent with general formula RMG, which R is the organic radical and alkyl, aryl, and exit halogen. These reagents react with great variety of compounds and are used to synthesize organic compounds. The Grignard reagent. Ethyl magnesium iodide, the electronegativity difference between the carbon in magnesium. So this carbon is partially negative charge and the magnesium is partially positive charge. In case of water, this hydrogen and oxygen also have the electronegativity difference. So attacks this negative charge on this hydrogen and this negative attracts in this magnesium and produces the ethane. Wurtz reaction. Chemical properties of alkane halogenation. When alkanes react with halogen with heat or light, hydrogen atom of alkane is replaced by hydrogen and alkyl halide is produced as product. This can be generally shown as mechanism of halogenation. The mechanism of halogenation occurs in the three steps: initiation, propagation, and termination. The chlorine-chlorine bond of elemental chlorine undergoes homolysis when irradiated with UV light, and this process yields two chlorine atoms, also called chlorine radicals. UV light, this is the free radical. Propagation step of chlorine radical abstracts a hydrogen atom from methane to produce the methyl radical. The methyl radical is torn abstracts a chlorine atom from a chlorine molecule and chloromethane is formed. The second step is propagation, also regenerates a chlorine atom. These steps repeat many times until termination occurs. Methyl radical and chloromethane. Termination takes place when the chlorine atom reacts with another chlorine atom to generate chlorine, or chlorine atom can react with a methyl radical to form chloromethane, which constitutes a minor pathway by which the product is made. The methyl radicals can also combine to produce ethane, a very minor product of this reaction. The reaction does not stop at this step, however, because chloromethane product can react with additional chlorine to produce polychlorinated products. Initiation, propagation, termination. Orientation of halogenation. To know the which one of the product is formed predominantly forming more than one product in the chemical reaction is called orientation. 45% 1-chloropropane, 55 2-chloropropane. The rate of abstraction of hydrogen atoms is always found to close the sequence at room temperature relative relates for hydrogen atoms. 1-chloropropane, 2-chloropropane, number of 1 degree hydrogen, number of 2 degree hydrogen, reactivity 1 degree hydrogen, reactivity 2 degree hydrogen, so 45 and 55.
Superimposable mirror image compound, a chiral that is no enantiomer. A superimposable mirror image means that one molecule could be placed on top of its mirror image and would fit perfect fit. It means the relative position of the atoms in molecule can be twisted without breaking bonds to make these molecules the exact same. Example, isopropyl chloride mirror image. See, this is the isopropyl chloride superimposable, no enantiomer. Non-superimposable mirror image compound, chiral, that is the enantiomer. Or non-superimposable mirror image enantiomer means that no movement about the axis can make these molecules exactly identical. They are exact opposite or your left and right in not superimposable enantiomers, chiral molecules. Chloroiodomethane sulfonic acid. Chloroiodosulfonic acid is the exact fits on this molecule on this mirror image. And this is the chiral. It does not exact fit, sorry, it does not exact fit this molecule on this mirror image and chiral, so it is the not superimposable on the enantiomer. Bonds in the simplest case compound with two similar chiral and carbon atoms to chiral centers where there is the same set of the four groups of each chiral center. The combination where the four groups are arranged such that the centers are mirror image of each other. That is the way the molecules has the internal mirror plane. That is the meso compound. See, mesotartaric acid and the half part of this compound, mesotartaric acid, is the order is the mirror image is order. Meso compound are optical inactive due to the internal compensation. The optical rotation due to the one half of the compound is equal and opposite to the rotation of due to another half and cancel its order. Mhm. Isomers of compounds with two dissimilar chiral carbon atoms, it is stereoisomers that are enantiomers, that is not a mirror image of one another and non-superimposable on one another. Such type of pair of stereoisomers which are not mirror image of each other are called diastereomers. Trichlorobutane 2 wall structure first and second trichlorobutane 2 wall, third and fourth structure first and second are mirror image and not superimposable. So first and second are enantiomers. But structure third is neither superimposable on first nor the mirror image on first, that is second. So pair of third and second are stereoisomers, but not enantiomers. In this way, third is diastereomers of first and second. Similarly, IV is also diastereomers of first and second. Diastereomers have also similar chemical properties, rate of reaction, diastereomers with a given reaction differently. Diastereomers have different physical properties like melting in boiling point. Diastereomers can have separated by fraction distillation in chromatography. Racemic modification or racemic mixture, when equal amounts of two enantiomers are mixed together, it gives an optical inactive form called the racemic modification or racemic mixture. It is denoted by using the prefix plus minus or RS, DL. Before the name of the compound, example, equal amounts of plus lactic acid and minus lactic acid. Resolution of racemic modification, the separation of racemic modification or mixture into enantiomer is called resolution. Mechanical separation or crystallization, it is adopted by the pasture for separating the enantiomers when racemic modification is crystallized from solution. We get two types of crystal which are mirror image of each other, consisting of plus and minus forms which can be separated by picking with the help of tweezers and powerful lens. Biochemical methods, certain microorganisms grow in the specific mixture. This newly grown microorganism consumes one of the enantiomers while leaving the another unaffected. Penicillium glaucum, when placed in plus minus tartaric acid, it consumes only plus tartaric acid, unaffected minus tartaric acid. Chemical separation in this method, the racemic modification is treated with optical active reagent to get a paired diastereomers. This diastereomers is separated by physical methods such as fractional distillation, crystallization, etc. Racemic modification of mixture versus plus minus acid, which is treated with minus base, gives mixture of salts. C plus minus acid minus base, salt of acid, base, salt of acid, salt of plus acid and minus base, salt of minus acid minus base. And are treated with S plus and enantiomer pure form, enantiomer pure form plus acid. S plus neutralizes minus base, S plus neutralizes minus acid. The transformation of optical active enantiomer into optical inactive racemic modification under the influence of heat, light, or chemical reagent is known as racemization. For example, plus or minus lactic acid when warming with sodium hydroxide converted to plus minus lactic acid. This is the racemization. Configuration is special arrangement of atoms or groups of atoms around a particular carbon configuration. The arrangement of atoms in space of molecules defined constant without regard to rearrangement that differ only as after rotation one or more single bonds defined as configuration. The spatial arrangement of atoms or groups of atoms around a particular chiral carbon is known as a configuration. So this definition clears that cis and trans isomers. Configuration, it is the actual arrangement of atoms in space. Relative configuration, it refers to correlative configuration, that is relative configuration, which relate configuration of one compound with other. Suppose a child has not learned to distinguish right from left and left from right given shoes. This child cannot be well tell which is right and which is left. That is absolute configuration of shoe. But the child may be able to tell that they are different in that they are fits one or his feet a but not another, and vice versa for the other shoe. In this way, child can determine the relative configuration of shoe. This is the absolute configuration. This is the comparison of two. This is the cis relative configuration. Sequence rule, the determination of absolute configuration is not so easy. And first method to determine the absolute configuration was developed by the Biswell-Canhol-Trelloc rules known as the sequence rule. Substance that has the higher atomic number take a priority over the lower atomic number. We'll first phase decide the relative priority of two groups. It is determined by similar comparison of text atoms in group and so on. In other words, if two atoms directly attached to the chiral center are same, the next atoms attached to each of these atoms are compared. Number one, highest atomic number is the carbon, and then after it has hydrogen, and then after it carbon. So this is second priority, in third priority, in fourth priority. If one of the atoms connected to the completing the chain has double or triple bond, that chain has higher priority. Number one, this is due to higher atomic number. This is the double bond with oxygen of the carbon, so second priority. And this is the third priority, and is the fourth priority. Specification convocation of RNAs in Kahn, Gold, and Prelog developed a method to design the configuration of all the molecules containing the symmetric carbon atom chiral center, which is known as the Kahn, Gold, and Prelog RNA system. Step 1. In this step, different atoms or group of atoms attached to the chiral carbon are assigned the sequence priority order sequence rule. After deciding the priority order of four atoms or groups attached to the chiral atom, then the molecule is visualized in such a way that atom or group of atom lowest priority is directed away uh, uh, us, while the remaining the three groups are priority towards us. Rectus or sinisters, if it is three groups in the order of their decreasing priority in clockwise direction, the configuration is spides reactors, and other hand decreasing priority in anticlockwise direction, the configuration is spied sinister or glyceride and S glyceride. See, this is the 1, 2, 3, and in the clockwise direction, that is the R glyceride. Is the 1 to 3 in the anti-clock, so S glyceride. Configuration on the basis of projection formula. When a compound is represented by a Fisher projection formula, the configuration can be easily determined without constructing model. To determine whether the I travels clockwise or anti-clockwise, we have to place the group or atom's lowest priority at the bottom of the Fisher projection formula. The atom or group of lowest priority at the bottom, in such case, simply rotate the I in the order of decreasing priorities. The configuration is R if the I travels in the clockwise direction and S if the I travels in the anti-clockwise direction. The R will right. If the atom or group of atom lowest priority is the top, in such case, rotate the molecules 180 degrees so as to bring atom group of lowest priority in the bottom. This can be done by reversing the position and all the atoms or groups. Then find the direction in the order of decreasing priorities as bromo, chloroidomethane. The top to bottom, bottom to top, left to right, right to left. The atom or groups of lowest priority is at the right hand side of the horizontal in case of seeing the position of atom groups clockwise direction. So that the group atom lowest priority comes at the bottom but not change the position of atom or group at the top of the vertical in. Then find the direction in the order of decreasing priority S bromochloroidomethane. This is the right inside in this stones, and top is the fix. So 1 to 3 S bromo hydrochloride methane. The group of atoms of the lowest priority at the left-hand side of the horizontal line, in such case, without changing the position of atom group at the top of the vertical in change the position of the other atoms groups anti-clockwise, so that the atom group of the lowest priority comes at the bottom, then to find the direction in order to decreasing priorities. R bromochloride methane. This is the left hand side, and top is the fix. So 1, 2, 3, 1, 2, 3. This is the clockwise. Configuration of compounds containing more than one chiral center. In such case, positive configuration about each of the chiral carbon is specified, and then with the alphabet numbers, the specification pertaining to the carbon atoms of that number is written 2R, 3R, 2,3 for trihydroxybutanol. See, in this example, uh, first number the atoms in the vertical way, 1, 2, 3, 4. For C2, this is the lowest is the left hand side. So 1, 2, 3. This is the 2R. Similarly, for C3, the lowest is the left hand side. It's the 1 to 3, 3R. Okay, electrophilic addition of halogen to alkynes. This is a triple bond, and this is the halogen. Electron density is the higher in the triple bond, and movement of electrons from triple bond to halogen, and withdrawal of this electron from this halogen, and forms like this the brominium ion. And then brominium ion is attracted by this bromide ion. So due to this the negative charge and the positive charge, and so on again, and forms this brominium ion. Again attacks this bromide ion, and tetrahaloalkane is produced. Similarly, in the chlorine, addition of water can react with the alkyne and produce propanone. This water is starts the electrons enol formation of the more substituted carbonium Markovnikov's rule. Again, this attacks and this carbon, and again enol tautomerization, deprotonate oxygen, alkyne ozonolysis mechanism. Okay, Thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience and wishes you all the best for your coming examination of BSc first year under Chemistry, Institute of Science and Technology, Tribhuvan University. Bye bye. See you again.